Hello Math 3311 students, let's begin lesson 10, arithmetic functions. An arithmetic function is a function defined in n or w. Here, n is a set of natural numbers, 1, 2, 3, 4, 5, 6, and so on, and w is a set of whole numbers, 0 and 1, 2, 3, 4, and so on. The function value can be either real or complex, or as a matter of fact, we can consider vector valued or matrix valued or whatever. But this is an undergraduate level math course, so we're going to focus upon just real valued arithmetic functions only. Let's see, do we have to consider some complex valued functions here? Probably not, but just for safety, let's leave it like that. We can denote those like this, n1, n2, n3 like this, if it begins from 1, or w0, w1, w2 like those, if it begins from 0. Now, haven't you seen these expressions before? You must have. Those are called sequences in analysis. Indeed, the arithmetic functions share the same definition as the sequences in analysis. As far as the definitions are concerned, they are the same thing. What makes a difference, however? The difference comes from the viewpoint, the focus. The arithmetic functions do not concern the limit and convergence. There are plenty of other things that we focus upon, but none of them have anything to do with limit and convergence. In analysis, on the other hand, almost all the time when you encounter a sequence, you look for limit and convergence. So that's a big difference. Now one more thing, and we're going to move on. Sometimes arithmetic functions are defined in z, but that's pretty rare. For example, if you have something like this, an arithmetic function defined from -2 and then -1, 0, 1, 2, 3, and so on, in that case, we can reduce it into another arithmetic function, a usual one defined from w, so that yn is xn minus 2, or xn is yn plus 2, equivalently speaking. So you can continue using this expression, and you can define this x as a shorthand of this, and then you can just go ahead without changing the definition of the arithmetic function. You can always go back to n or w, so no problem. Now, what if you have a double-sided sequence? In this case, it's going to be a little bit harder to use these typical definitions of arithmetic functions, so we have to put those two together. For non-negative indices, an is same as xn. For negative indices, that is x of negative n, then we define those as bn, and then combine those two together. And of course, if you want to start from 0 here, you can do that too, just that a0 and b0 are the same. So in short, you don't really have to define it in z, because we can always reduce any kind of expression like this into a pair of arithmetic functions based upon the previous definition. So we are going to stick to this as a definition. And that's about it for the definition. All right, one done. Let's go to the next topic. Let's look at some examples. Here are a couple of examples. I should say the simplest pair of examples, the simplest non-trivial pair of examples, maybe the simplest pair of examples with some interest, some importance, or whatever we may want to call. Tau of n is the number of positive divisors of n, and sigma n is the number of all positive divisors of n, so sum of all positive divisors of n. For example, what is tau of 10, for example? Let's see, 1 divides 10, 2 divides 10, 3, 4, no, 5 divides 10, and that's it, isn't it? We successfully counted them all. So tau of 10 is 3. Is that clear? How about sigma of 10? 1 divides 10, 2 divides 10, and 5 divides 10, and there's no more, right? So adding them all up, sigma of 10 is 8. And then you can calculate sigma and tau values for every positive integer. So this tau and this sigma define an arithmetic function defined in n. N goes from 1, 2, 3, 4, and so on. Sigma of 0 or tau of 0 are not well defined. Now let's go one more step. Our textbook does not deal with this, but it just, not even one step, half a step, so let's talk about it. Let's generalize this just a little bit. Not just the sum of all positive divisors, but sum of the kth power of positive divisors. In other words, for example, what is sigma 3 of 10? 1 divides 10, but third power. 2 divides 10, but third power. 5 to the third power. So what do you have? 1 plus 8 plus 125. That's 133, 134. You can calculate like this. And of course, if k value is not an integer, then we have a bunch of radicals to add, so things are more complicated, but at least I hope you can see this expression. This is a real reason I'm introducing this extension here. So what do you mean by this sigma sub k of n? It's a sum of all expression d to the k power, where d divides n is positive, the sum of kth power of all positive divisors of n. In a special case, when k is 1, then you don't have this, just adding all d's whenever d divides n. So we have the sum of all positive divisors of n. So we have sigma n is the same as just sigma 1 of n. So sigma k of n is actually a little bit of a generalization of this. Furthermore, it's a generalization of this as well. How? Put k 0 and this entire thing is 1. So for each positive divisor d that divides n, add 1. So adding 1 each time, what is that? That's the same as counting. And this is given by counting. And that's how these two are related to sigma k of n. Okay, we just went one step further, maybe half a step further than our textbook, but I think it was well worth it. You can get a combination and the relation between those two. Now, next example, Euler's totient function. Wow, this is important function. We already encountered it in lesson 9 when we dealt with Euler's extension of Fermat's theorem. V of n is the number of positive integers less than n that are relatively prime to n. Well, we've been dealing with 10 so far, so V of 10, what is it? Let's see. So what do you have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Among those, 1 is relatively prime to everything, so okay, there you go. 2 is not relatively prime, no. 3 is relatively prime to 10. 4, 5, 6, no, they are not relatively prime, they are all out. 7 is a prime number, so that's relatively prime to 10. 8, no. And finally, 9 is relatively prime to 10. So we have, there are 4 such numbers. So that's an example of an arithmetic function, and phi of n is probably the most important of the bunch, Euler's torsion function. Finally, another example here. Given prime number p, the p-adic valuation function is defined like this. Nu p of n is the highest power of p that divides n. What does it mean? Well, if you do the prime factorization of n, and yes, you can do that uniquely thanks to the fundamental theorem of arithmetic, then n can be expressed as a bunch of prime factors to some powers. That power is what this valuation is looking for. For example, 24 is 8 times 3. So that's 2 to the third power times 3 to the first power, isn't it? And then if you do nu2 of 24, and that's 3, this power. If you go to the 4 or higher, then 2 to the 4th power or higher will not divide 24. That's the biggest you can get. You're looking for that number there. Nu3 of 24 is 1, as you can see over here. And then nu p of 24, well, we're going to get over 0 as long as p is 2 or 3. Any prime other than 2 or 3, you're going to get 0 because otherwise you don't have anything. Or even if something is there, say 17 to the 0th power, yeah, we get 0. I selected this example because the fundamental theorem of arithmetic is such an important thing for number theory, and this example is directly related to that. But otherwise, I don't think we'll ever come back to p-adic valuation function. It's an interesting thing to study, but at this level, yeah, that's a bit too much. So we went through an example, that's good, all right. But other than that, well, okay, I don't want to completely remove it from our consideration, so let's keep that. So we studied 1, 2, 3, 4. Yeah, there are 4 important examples of arithmetic functions. Among them, the last one is relatively less important at our level because we are in undergraduate level. And then instead of this p-adic valuation, another one will come from section 3, Möbius function, mu, and that's going to become a little bit more important, but at this level, let's not talk about it. We're going to talk about section 3 in lesson 11. Let's see, do we have enough time for one more? Sum and product. Okay, all right. Okay. Tau of n, which is the number of positive divisors of n, can be written as sum of ones. You see, adding ones each time d divides n, it's just a counting. Each time a positive divisor in d appears, add 1. So it's just a counting. Therefore, this summation is same as counting, and this one is counting function. So tau of n. Now sigma n, this time we just add up that very d, so we get the sum of all positive divisors. So as you can see, tau of n and sigma n are related to summation expression. Now from fundamental theorem of arithmetic and prime factorization, we can express any n as prime factorization, but the power, those are p-adic valuation. So from the fundamental theorem, we get product expressions like this too. So many times we are going to encounter sum or product expression of arithmetic functions. So it may be a good idea to pay attention to those, especially the sum.